Hello. This lecture will cover pages 25 through 28 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on resistive circuits, Chapter 2C, series circuits, and the voltage divider rule. We're going to start out on page number 25. We're going to talk about, of your lecture notes, series circuits. There are three different types of circuits that we're going to look at in general. There's series circuits, there's parallel circuits, and then through most of the course we talk about a combination of series and parallel circuits combined. So first of all, let's look at the simple series circuit. A series circuit is defined by a circuit whose portion of the circuit with only a single path for charges to flow. A circuit or portion of a circuit with only a single path for charges to flow. Here's an example of a series circuit with three resistors in it. We have a source of EMF, 9 volts. I made up a voltage here. And we have three resistors, R1, R2, and R3. I want you to notice that the total current flowing in this circuit is this current here. The current gone through resistor R1 we're going to label I1, the current through resistor R2 we're going to label I2, and the current through resistor R3 we're going to label I3, but I total is equal to I1, which is equal to I2, which is equal to I3, because it's like water in a hose. If you have 5 gallons a minute at this point, and this is one continuous hose, you have to have 5 gallons per minute flowing in every portion of that hose if it's free running. The total resistance of that circuit, looking in here, and I even labeled this, I put R sub T. If you're right here on this battery and you're looking to the right here, you're looking into the circuit, what are you going to see in terms of resistance? You're going to see the 100 plus the 300 plus the 50. You're going to see a total of 450 ohms. So this circuit can be simplified down to a 9-volt battery and one resistor of 450 ohms. The total current then, once you find the total resistance, is the total voltage driving the circuit, 9 volts divided by RT, 450. It's 0.02 amps, and we know that's 20 milliamps. So there's 20 milliamps flowing in that circuit. Characteristics of a series circuit. How do you know you have a series circuit? When you do, what are the characteristics of it? The current is the same at all points in the circuit. That's a characteristic of a series circuit. And you can see that from up here, and I explained it. The total resistance is given by the sum of all the resistances. I explained that up here. By Kirchhoff's voltage law, the applied voltage is equal to the sum of all the individual voltage drops. So if you take a look, using Kirchhoff's voltage law in a series circuit, up here, this source of EMF, the applied EMF has to equal this drop, this drop, this drop, and you're back to 0. That's what that says. And by the voltage divider rule, the voltage drop across a particular resistor, let's call it Rx, is the total applied EMF times this ratio of Rx over the total resistance. This voltage divider rule is going to be a very nice rule for you to use to solve problems all the time. So I'm going to explain what we mean by the voltage divider rule. If you look on page number 26, the voltage divider rule. Very important, have 2 stars on it. Finding the voltage across any resistor or combination of resistors in a series circuit can be reduced to a single step. Wow, who doesn't like a single step? Let's take a look at this circuit here. I drew a source of EMF with 3 resistors. X is 1 here, there's a 1. X is 2 here, there's a 2. And X is 3 here, there's the 3. The corresponding current through R1 is the current I1 is V1 over R1, assuming if you know the voltage V1. The current through R2 is the voltage across R2 divided by resistor R2, and the current through R3 is the voltage across R3 divided by R3. Well, since the total current is equal to I1, is equal to I2, is equal to I3, you can say that that total current, E over the total resistance, E over this total resistance, this plus this plus this, that's the total current. And pick any one of these, Vx over Rx, because these are all the same. So just take a look at this and make sure you understand how I get this equation. That's fundamental in understanding how the voltage divider rule is going to work on this next page. So what is the voltage divider rule? The voltage across any element, the voltage across R1, V1, R2, V2, R3, V3, is equal to the total voltage E times the ratio of the resistor over that particular resistor or resistors, if you want voltage across more than one resistor, divided by the total resistance. So you're going to use this a lot. Not just for homework. You're going to use it for all through this course. It's called the voltage divider rule. But take a look at what it really is doing. It reduced finding the voltage across an element to one step, but take this RT and just put it out here. Take this RT and write it out here. That's the total. E over RT is the total current. And if you take the total current times the resistance value, you're going to get the voltage across that resistor. So it's nothing magic. We're just moving that RT in here. Make sure you understand that. But let's use this now. Over on page number 27, I have a nice example to look at here. Example. In the series circuit shown below, use the voltage divider rule to find V1, V2, VA, and VZ. So I want you to use the voltage divider rule and see if you see how I got these down here. Let's take a look at it. V1, the voltage across the resistor R1, what's it equal to in a single step? It's equal to the total voltage in the circuit, 15, times the ratio of 2 over the total resistance, 2 over 10. That's 3 volts. There's 3 volts there across this, plus to minus, as current flows from left to right. What about V2? Well, it's the total voltage, V, 15 volts, times the resistor. We want it across V2, that's R2, times 3, divided by the sum of all the resistances again, 10. It's 4.5 volts. Let's do it over multiple elements once. So what about VA? What's the voltage from this point to this point? What if we wanted to know the voltage here to this point, this being a reference? Well, it's the total voltage, 15, times the sum of these two resistors here. Treat them as one resistor, 3 plus 2, divided by the total resistance again. It's 7.5 volts. And here's VZ. What about the voltage between these two, across these two? Total voltage 15 times the sum of these two resistors divided by the total resistance. It's 9 volts. Once you find these, you can check your answers. You have tools in your toolbox, we're going to call them. We're starting to build up some nice tools. Well, what tool can we use to check this? That's Kirchhoff's voltage law around the loop. We've already made calculations, so just take plus E minus V1 minus V2 and then minus A, because we already found A from here to here. We do these two at the same time. Minus A. Does it equal 0? Put these in, and if it does, you know that these were done correctly. That's the voltage divider rule. On page number 28, I have an example problem. It's one of your examples in the book. I think it's example 216 in the book, but let's take a look at it here real quick. Example, for the DC transmission facility model shown below, and I drew a model, find VS, the source voltage at the generator, and the power loss in the line. We're going to call that R sub L. The line resistance we're going to call R sub L. Now before we start working these numbers, and it's just Ohm's law stuff here, I want you to notice that from this facility here, if we did have a DC transmission facility somewhere, it's going to be miles. This could be 20 miles from here to here. But that's line resistance. That's a bunch of line resistance across 20 miles. We're going to group it all together, and we're going to call it as one resistor to model this. We're going to call this, the line resistance is 20 ohms. And they're giving you that the load resistance is 220 ohms, and they're giving you the load voltage is 458.3 kilovolts. That's thousands of volts. So what they want you to find here is the source voltage, VS, and the power loss in the line. Well, you know you have to get the current. It's I squared R. But to solve this problem, I always draw a picture, and then I looked for where do I have 2 out of the 3? I mean, you know Ohm's law, V equals I times R, and its derivatives. If I could find 2 out of those 3, voltage, current, resistance, I can find a third, and then I can start analyzing the problem. Well, if I drew the picture like I want you to do, look, here's your load. You know the resistance of the load, you know the voltage across the load. There's your 2 out of the 3. You can find the current. Once you find the current here, you know it's the current here. That's what I did. The current in the load, 2.083 kiloamps. Yeah, that'll kill you in a heartbeat. But this is what power's all about. 2.083 kiloamps. The line voltage then is Ohm's law. If you have that current flowing through this 20 ohms, you end up with 41.66 kilovolts across that. And then using Kirchhoff's voltage law around the loop, I could find the source voltage here. It's 500 kilovolts. I can use the voltage divider rule to check my answer. There's the voltage divider rule for the load voltage. So I just substitute in that 500 here, and I work this out, and I see if I can't get this voltage, if I can't get what they gave me based on what I calculated here, just use the voltage divider rule, and you'll see that it works. Then the power in the line that's given off in the form of heat, you can calculate it this way, you can calculate it this way. 2 different ways of calculating it. It's 86.79 megawatts. 86.79 megawatts of power given off in the form of heat on this 20-mile distributed line. You ever wonder why the birds are sitting on the lines in the wintertime? They're keeping warm. In any event, look at page 41. They pull out they make a good comment here on page 41. And I'm going to read it to you because I think it's pretty informative. Since power can be calculated as V times I, suppose now that the utility company supplied power at, let's say, some value, let's say 200 kilovolts and 4 kiloamps. Different problem. What effect would this have on the transmission network? Without making a single calculation, we know that because power is proportional to the square of the current, there would be a large increase in the power loss in the line because you have much more current, and therefore the efficiency of the facility would decrease substantially. That's why in general we transmit power at very high voltages and low currents. That goes for AC too. That's why out on these transmission lines that go across the country and even out on the streets outside your house, they're 12,000 volts. They're 12 kVA. They're distributing local voltage at local current and voltage at very, very high voltages. And why are they doing that? Because if they kept the voltage down and they got the current high, because look, in power, when you're calculating power is equal to V times I. For a fixed power, you can make this large and this small, or make this small and this large for a fixed amount of power you want to deliver. Well, we know power is equal to I squared R. That's power loss. So the higher the power is, the higher the current is, you square it. And it contributes to a lot of power loss for a fixed resistor in the line. So for a certain amount of power, you want to keep the voltage high, keep the current low, because you're squaring the current to get the power. I think that's pretty informative. See example 215. If you look here, example 215, that's a pretty good example, but it's pretty easy. In the textbook, there it is. I don't know if it focuses very well. But I want you to make sure you can find I, VBD, and the power absorbed by that 30 k ohm resistor. And then they use the voltage divider rule to find VBC. They do it here, and they work it out. But you should be able to work that out pretty easily and then just check your answers. And then the learning assessment. I like to work a few of these, and we'll try to wrap this up in 2 minutes so we get under 17 minutes in this video. But we're looking at, let's see where I worked that out. Learning assessment E210. I want you to look at it, and there's my solution. They give you the circuit and they say find I and find VBD. Well, you have a lot of tools in your toolbox, but at this point you have to find I first. You have to find the current, and then you can find VBD. If you try to go after finding VBD first, you can't get anywhere. So that's why the author's sort of leading you here in these first chapters. You know, they're saying find I, then find VBD. So first, around the loop. Loop 1 by Kirchhoff's voltage law. There's the equation starting at this point, just going around the loop. What's the voltage drop up here? You could call it V sub 80 k ohm, you know, but let's just skip that step. If we know the current I is flowing here, it's flowing here. It's a series circuit. So this current I that they give you, it's flowing through everything. That I flows the whole way around this loop. So the voltage there is 80 k I. 80 k times I, that's Ohm's law. And it's a minus because it's a drop. Minus 12, minus 40 k times I again. 40 k times I, that whole thing is... So you end up with one equation with one unknown. I is a negative 0.05 milliamps. What it tells you is when you see a negative current, it means this current really doesn't go in that direction. It really goes up. But if you show it as a negative here and you show the arrow going down, I'll know that on an exam. Then when you find I, then you can basically go around loop 2, which is a loop that I defined right here. Loop 2 goes from here, look. Right there. That's loop 2 right there. VBD. So I cut it off right here and I call that VBD plus the minus because B's first. There's the equation. We worked this out before. VBD, 10 volts, you're done. And then 211. That example, that assessment problem 211 right there. You should be able to work that out using the same technique we did in 210. And that concludes this lecture.